So let's look at some examples of expectation. We'll start off with example 39. Here the experiment is to flip two distinguishable fair coins, say a quarter and a nickel, and record the up faces. Then let the random variable x be the number of heads shown. Now we have looked at this example before. We found the PMF of x, we found the CDF of x, we looked at the graphs of the PMF and the CDF. And so now what we want to do is compute the expected value of x, in other words, the mean of the distribution of x, the variance and the standard deviation of x, as well as the skewness and the kurtosis of the distribution of x. All right, so we'll start off by computing the mean of the distribution. So the mean of the distribution of x, which is also given by the expected value of x, by definition, is the sum over the values of x in its sample space of x times f of x, which is the PMF of x. So the mean, the expected value of x, is a weighted average of the values taken on by x, the weights being the values in the PMF, which are the probabilities that x takes on the particular values. Now the values of x in the sample space are 0, 1, and 2, and so this is the sum, x going from 0 up to 2, of x times f of x. And so we have 0 times f at 0, plus 1 times f at 1, plus 2 times f at 2. Now 0 times f of 0 is 0, so that goes away, and so we're left with 1 times f evaluated at 1, plus 2 times f evaluated at 2. Now remember that the PMF evaluated at 1 is 1/2, and the PMF evaluated at 2 is 1/4. So we have 1 times 1/2, or 1/2, plus 2 times 1/4, which is 1/2. And so the mean of this distribution is 1. Now remember that the interpretation of the mean of a distribution is that the mean is the center of mass of that distribution. It's the balance point of that distribution. Now, the fact that the mean is equal to 1 in this case should be no surprise, because if you'll think back to what the graph of that PMF looked like, it was a symmetric distribution with the rectangles centered over 0, 1, and 2, and the modal bar, the highest rectangle, was 1, and so the distribution was symmetric about 1. It was symmetric about 1, and that would have been its balance point. So there's no there's no surprise here that the mean of this distribution is 1. Now let's calculate the variance of the distribution. So by definition, the variance is the expected value of the square of the difference between the random variable and its mean. Now the mean is equal to 1, all right, and so we have the sum over the values of x in the sample space, x minus 1 quantity squared times f of x. All right, and remember that the values in the sample space are the integers 0, 1, and 2. All right, so this is the sum that we're going to calculate. And I'm going to use the definition formula here. This is a simple enough example where the definition formula is straightforward to use. And so we have, this would be equal to 0 minus 1 quantity squared times f at 0, plus 1 minus 1 quantity squared times f at 1, plus 2 minus 1 quantity squared times f at 2. So we have minus 1 squared times 1/4 plus 0 squared times 1/2. So that term is going to vanish. Plus 1 squared times 1/4. So obviously we have 1/4 plus 1/4, which is 1/2. So the variance of this distribution, the variance of x, is 1/2. The square root of the distribution, the square root of x would be the square root of 1/2. Now to calculate the skewness coefficient, we'll first calculate the third central moment. So by definition, the third central moment is the expected value of x minus mu all to the third power. And so that's going to be the sum over the values of x in the sample space, x minus the mean, which remember was 1. We cube that difference and then multiply that cubed difference by the PMF. And so we have 0 minus 1 cubed times f at 0 plus 1 minus 1 cubed times f at 1 plus 2 minus 1 cubed times f at 2. And so we have negative 1 cubed times 1/4 plus 0 cubed times 1/2 plus 1 cubed times 1/4. Now, negative 1 cubed is negative 1. Multiplied by 1/4, that's negative 1/4. Then we have a positive 1/4 over here, so the third central moment is 0. To get the skewness coefficient, we divide the third central moment by the variance raised to the 3/2 power. And since that's positive, then the skewness coefficient is going to be 0 because the numerator is 0. So this implies numerically, quantitatively, that the distribution of x is symmetric about its mean, which we already knew because we've seen the PMF. And then finally, we'll calculate the fourth central moment, and from that we'll calculate the kurtosis of the distribution of x. So the fourth central moment, the expected value of x minus mu raised to the fourth power is 0 minus 1 raised to the fourth power times f at 0, plus 1 minus 1 raised to the fourth power times f at 1, plus 2 minus 1 raised to the fourth power times f at 2. And so again, we get 1/2. And so the kurtosis is 1/2 divided by the square of the variance. The variance was 1/2, and so we square that, we get 1/4. And so it turns out that the kurtosis for this distribution is 2. And so to summarize everything, the mean of the distribution is 1, the variance is 1/2, therefore the standard deviation is the square root of 1/2. The third central moment was 0, and the fourth central moment was 1/2. And then from these quantities, the last three quantities here, we get the skewness and the kurtosis. The kurtosis of the distribution is 0, indicating it's a distribution that is symmetric about its mean, and the kurtosis is equal to 2. Now let me show you another way to go about calculating these things, which is going to be useful to us, especially in this course, when we are looking at more complicated situations than this one, and we're dealing with discrete random variables. So what I've done here is create a spreadsheet, and in that spreadsheet, in the first two columns, I have the PMF of x. In the first column, I list the values in the sample space. So in this case, 0, 1, and 2. In the second column, I have the values that the PMF takes on. So 1/4, 1/2, and 1/4 corresponding to the values in the sample space. And then I've got four additional columns. And the reason for calculating these particular four columns is because I'm using expansion formulas to calculate the second, third, and fourth central moments. You've seen the expansion formula for the second central moment, which is the variance. You have not yet seen expansion formulas for the third and fourth central moments, but you will later in a subsequent lecture coming up, and also in the third lab assignment, you'll actually prove those expansions. I could just as easily have had columns here that would allow me to calculate these central moments directly. But just understand the reason that I've chosen these particular four extra columns is because I'm using the expansion formulas to calculate the second, third, and fourth central moments. So in this third column, I've got values of x times the PMF. So the product of the first two columns. So 0 times 0.25 is 0, 1 times 0.5 is 0.5, and then 2 times 0.25 is 0.5. And then I have the column total, all right? And then in this fourth column, I've got values of x squared times f of x, and I have the column total for the fourth column. And likewise, I have these last two columns. In this column, I've got values of x cubed times f of x, and then I've got x to the fourth times the values of the PMF in this column. And then I have the column totals for each of these columns. And so let's look at this value here. this is the sum of x times f of x. And so this is the expected value of x, or the mean of the distribution of x, which I've listed down here. This value, 1.5, this is the sum of the x squared values times f of x. And so this is the expected value of x squared. Okay? Now remember the expansion formula for the variance. We also call it the computational formula, or the shortcut formula. And so remember that if you take the expected value of x squared, and then from it subtract the square of the expected value of x, you get the variance. And so we have 1.5 minus the square of 1, which itself is just 1. So that difference would give us the variance, which is 1/2. And so that's what we have here. Now, this column total, this is the sum of the values taken on by x cubed times f of x. And so this is the third raw moment, the expected value of x cubed. And then finally, this 4.5, this is the sum of the values taken on by x to the fourth times f of x. All right, so this is the fourth raw moment, the expected value of x to the fourth. And from these raw moments, we can get values for the skewness and the kurtosis. But just notice that we get the same values for the mean, the variance, the skewness, and the kurtosis that we obtained using the definition formulas and doing it by hand for this simple example. But if we had, let's say, a discrete random variable that had many more values comprising its sample space, then doing the calculations by hand would be tedious and cumbersome and prone to error, at least the potential for error. And so if we have a spreadsheet like this that's programmed in, so these columns are all these cells are all programmed to calculate these stated products. And then, these column totals are programmed to calculate the column totals. And then these cells down here, these have programmed in them the expansion formulas from which to get the various quantities. So if we have a spreadsheet like this, it's going to make our life much, much easier when we're dealing with examples, lab assignment problems, and so forth, that deal with more complicated discrete random variables. So this is one way to calculate these quantities, and I would encourage you to create your own spreadsheet like this, because then all you have to do if you want to use it for a different example, a different problem, all you've got to do is increase the number of rows, for example, and then make sure that you carry over the formulas in the appropriate way. Now, I also want to show you a convenient way to do these calculations in the TI-84 calculator. And if you've got a calculator that does list calculations, then you should be able to do the same kind of calculations in it. Now, let me bring up the emulator here. And what I want to show you is I'm going to stat, and then I'm going to look at my lists. And so what I've done here is I've entered in list 1 the sample space of x, 0, 1, and 2. And then in list 2, I've entered the values taken on by the PMF. So 0.25, 0.5, and 0.25. All right? And then what I'm going to go back to get out of the list editor, and I'm going to invoke list functionality. And now remember that the mean of the distribution is the sum of the x times the f of x values. All right? And so I can go into list. Remember, this is the list functionality, so second and then stat button. And what I want to do is I want to multiply corresponding values in list 1. I can choose list 1 this way. I can also select it that way, so list 2. So I want to multiply corresponding values, corresponding entries in list 1 and list 2. And when I do that, I get a new list. Okay, 0, 0.5, and 0.5. Well, the mean of the distribution is the sum of that set of values. And so the one way that I can do this very easily is second list, go to math functionality, and then I want option 5, which is the sum. Now I want the sum of the values taken on by the products of the corresponding entries in those two lists. And so I get 1. And so this would be the mean of this distribution. Okay, now let me show you how to calculate the variance. And so remember that the variance, by definition, is the sum over the values in the sample space, in this case 0, 1, and 2, of x minus its mean 1, quantity squared times the values in the PMF. All right, so let's build a list first and then calculate the sum of the values in that list. So I want the values in list 1, the sample space, minus, okay, the mean, which we just found to be 1. I'm going to square those deviations and then multiply by the corresponding values in the PMF. That's going to give me a new list. I want the sum of those values. And so let me go up here and grab that expression. I don't have to retype it. And so I get 0.5 or 1/2. Right? So that's a really convenient way to calculate the variance. But now let's next calculate the third central moment. Well, that's going to be very easy. Now that we've got the variance, all we have to do is scroll up here, grab that expression, and then we can modify that expression by changing the exponent from 2 to 3. And so now we have the third central moment. Now, if we divide this by 1/2 raised to the third power, we get the skewness coefficient, but we know that's going to be 0. Finally, let's calculate the kurtosis. To do that, we'll first calculate the fourth central moment. And so I'll grab that expression, and we're going to change the exponent here, the power, from 3 to 4. And now I can just press enter, and I get 0.5. Now remember that the kurtosis is equal to the fourth central moment divided by the variance raised to the second power or squared. Okay? And so we get 2. And that is exactly what we calculated for the kurtosis when we calculated it by hand and also using the spreadsheet. Okay, so this is one characteristic or attribute capability of the TI-84 that I really, really like. I really like the list functionality that this calculator provides because it really helps to calculate these quantities for discrete random variables. So that's the end of this example. I think I'll stop this video and we'll pick up the next example in a new video.